So today we get to start Unit 2 right on schedule here. In Unit 2, we are looking at relationships between more operations. Now, we've seen our operations come in pairs so far. For example, we had addition and subtraction. And these are what we call inverses, because one of them undoes the actions of the other. So I pick a number between 10 and 20. 15, okay? Somebody else pick a number between 5 and 10. 5. So if I take 15 and I add 5 to it, what do I get? 20. If I want to take that 20 and get back to the 15, what do I have to do? Subtract 5. So we see the addition and the subtraction, adding 5 and subtracting 5, end us up right back where we started. We can do it the other way. If I started with 15 and I subtract 5, what do I get? 10. Well, what if I wanted to take that 10 and turn it back into a 15? What do I have to do? Add my 5. So subtracting 5 and adding 5, again, no matter what order, they reverse each other. They're inverses. Another set of inverses, of course, is multiplication and division. And they work the same way. If we start with 15 and I multiply by 5, what do I get? 75. And if I take that 75 and I want to turn it back into a 15, I would divide by 5. So again, multiplying by 5 and dividing by 5 take us right back to where we started. Or if I take my 15 and I divide by 5, I'm going to get 3. And if I have that 3 and I want to get it back to a 15, I need to times 5. So again, no matter what the order, dividing by 5 and multiplying by 5 take us right back to where we started. There's another set of inverses that we looked at a little bit, and that was our exponents, or powers, and roots. Remember, both of these combine to make exponents. So let's take something like 6 to the power of 2. That's a power. What does that equal? 36. If I want to take that 36 and turn it back into a 6, what do I have to do? Square root. Very good. We would square root that 36. Now, of course, there's an issue with that. That square root of 36 can be 6, or what's the other possible answer? -6. Because 6 squared and -6 squared both equal 36. So when we square root, there are 2 possible answers. Most of the time in the real world, we're looking for that positive result because most things in the real world are positive. Electronics is one of the few areas where that negative result is often relevant. How about if I have 5 to the power of 4? What's that equal? 625. What if I want to take that 625 and turn it back into a 5? Power of 4, so this would be 4th root, right? A 4th root reverses a power of 4. These are inverses. One undoes the other. Now, likewise, I can go the other direction. Now, of course, by the way, this is 5, or what else could this be? -5. because negative 5 to the power of 4 would also be 625. While I'm at it, let me show you one more example of that. Come on. How about 8 to the power of 3? What's that equal? 512. Very good. If I want to get from that 512 back to 8, what do I do? Power of 3, so it's going to be a third root. Notice the pattern here, by the way. The index here on the root matches our power and our exponent. Except for up here, the square root, there's no number written here. That's implied to be a 2 because it reverses a square root, or a power of 2. Now down here, would this be 8 or negative 8? Just the positive, because negative 8 to the power of 3 is actually negative 512. So where we have this two possible answers of being a 5 or a negative 5 is only on the even roots, the even index of the roots. It does work the other way, by the way. If I have I'm asking for the fifth root of 243. Do you guys know how to calculate that in your calculators? Many of you have like an X root key. It's the second function over your caret key or your power key. So you put in the 5 first, the X root, and then 243. Did you get 3? What'd you get, Josh? Or Jordan. You did get 3? You said that looked like it didn't work. So. Okay. Everybody got it? No? Yours, I believe you have to go through the math menu. Did it work? Gotcha. So we go the other way. 3 to the power of 5, of course, is going to give us 243. I want you to try this one, the 11th root of 2048. See what you come up with. Got her to come up to good. So those powers and roots are inverses. Now remember what we said when we were dealing with addition and subtraction and with multiplication and division in the first week. Because they're inverses, because they go together, any rule that applies to one applies to the other. The same type of thing goes for our powers and our roots. Any rule that applies to a power also applies to the root. And we'll take a look at how that works. Now, some of these basic rules for powers we've already seen. For example, x to the 5th times x to the 9th. What's that going to be? X to the 14th. Good. 5 plus 9 is 14. When we have a power, an exponent like this, remember an exponent has two pieces. We have the base, which is this number right here. Then we have the power. When an exponent, when we're multiplying exponents that have the same base, these are both x, we can add the powers. 5 plus 9 is 14. What about if we're dividing x to the 12th divided by x to the 7th? We get x to the 5th. Good. And that is found by just taking 12 minus 7. When we divide, we're subtracting powers. Again, as long as we have the same base. that look familiar? So how about x to the 5th to the power of 9? What's that going to be? X to the 45th. Good. When we take a exponent to another power, we multiply the powers together. 5 times 9 is 45. So let's take a look at what happens if it's a little bit more complex than that. First of all, what's x to the power of 0? 1. Anything to the power of 0 is 1. At some point, you may see a question on a quiz. It might even be an extra credit question. It looks something like this. What's that equal? 1, because all the power is 0, yes. So be aware of that. That simplifies things. What does it mean to have x to a negative power, x to the negative 3? Well, if you recall, x to the 3rd, it's easier to do this with numbers. Let's do it as a 10 to the 3rd is 1,000. 10 squared is 100. 10 to the 1 is just 10, right? Each time, we're keeping that base the same, the 10, but each time we reduce that power by 1, our number here was divided by 10. That's why when we got to 10 to the 0, 10 divided by 10 is just 1. But if we keep going with that, 10 to the negative 1, we have to divide by 10 again. That's 1/10. 10 to the negative 2 would be 1/100th. 10 to the negative 3, 1/1000th. And what we notice here is there's a connection between 10 to the 3rd and 10 to the negative 3rd. They're just reciprocals. 10 to the 3rd is 1,000, 10 to the negative 3rd is 1 over 1,000. Or 1 over 10 to the positive 3. Now, since x to the negative 3 really isn't, you can't calculate anything out there, all we can really do is say x to the negative 3 is equivalent to 1 over x to the 3rd, the reciprocal of x to the 3rd. So, how do we do calculations with combinations of variables? Let's say we have xy to the power of 6. That means we're going to have 6 xy's multiplied together, doesn't it? Well, as we saw at the beginning of last semester, one of the properties of numbers we have when it's all multiplication, and this is all multiplication because this is just x times y for each of these as well. We have what's called the commutative property. We can change the order. So what I can do is I can move all of these x's together up here. And then I can put all the y's together. And what I have is, here I have 6 x's multiplied together as x to the 6th. Here I have 6 y's multiplied together, which would be y to the 6th. So x to the 6th, y to the 6th. What happens is when I have two things being multiplied here, and I take that to a power, I can do the power of each piece separately. X to the 6th, then y to the 6th. So what that means is I can have x to the 5th, y to the 9th, to the power of 4, and I can do each piece separately. Darn it. What's x to the 5th to the power of 4? X to the 20. 5 times 4 is 20. Y to the 9th to the power of 4. 36. 9 times 4 is 36. it also applies if we put numbers on there. I can do each piece separately. Now we got to be careful here. 3 to the power of 4 is not 12. We actually have to do that power. That's 4 3's multiplied together, which is 81. X to the 7th to the power of 4 is x to the 28th, and y to the 3rd to the power of 4, y to the 12. What do you think? We could have a fraction, x over y to the power of 3. That's just x over y, 3 of them multiplied together. But when we multiply fractions, we're just going to multiply numerators. What's x times x times x? X to the 3rd. And y times y times y? Y cubed, or y to the 3rd. So we can see what happens there when we're taking a power of a fraction. We can just do the numerator to that power, then the denominator to that power. So if I have x to the 8th over y to the 3rd to the power of 5, I can do x to the 8th to the power of 5 is going to give me x to the, what's 8 times 5? 40. And y to the 3rd to the power of 5 is going to give me y to the 15th. Very good. So we can combine these powers and exponents in all sorts of different forms. Now, how does that translate into roots? If I had xy to the 5th power, I could do x to the 5th power and then y to the 5th power, right? If I have the nth root of x times y, I can do the same thing. I do the nth root of x times the nth root of y. This comes in kind of handy if you're working with larger numbers. Now we have the calculators now, which means we don't have to do a whole lot of thought when we do roots anymore. But you might run into something like this. Just a square root of 36. Now, many of us know that the square root of 36 is 6. But if we didn't, we might be able to write it like this. 36 is 4 times 9, correct? So the square root of 36 is the square root of 4 times 9, or the square root of 4 times the square root of 9. Well, what's the square root of 4? 2. What's the square root of 9? 3. 2 times 3 is 6. So the square root of 36 is 6. Now again, most of you knew that the square root of 36 was 6. You didn't have to break it up like that. And for this course, you'll just punch it in your calculator. But if you guys were to go on to a 4-year degree at some point, you're going to have to take an intermediate college algebra or a college algebra class. And in that type of class, you would look at things like this. You might look at something like a square root of 72. Now, if you punch in the square root of 72, you're going to get 8 point something, like 8.5, something really ugly. But we can split it up like this. 72 is equal to 36 times 2, correct? Yeah, so the square root of 72 can be thought of as the square root of 36 times 2. Well, we can split that up into the square root of 36 times the square root of 2. We know that the square root of 36 is 6. So you can actually write that as 6 times the square root of 2. What that does is allows you to keep it in, it's called exact form. If you punched in the square root of 2, you get 1.404, and so on. Well, leaving it as 6 times the square root of 2, that is an exact answer that you can use later. Other things that work with our exponents that also work with our roots. And by the way, this works with other roots too. It doesn't have to be just a square root. We could do, like a cubed root of a what? A triple root? Quadruple root? Fine, we'll do a fourth root. Just for Jordan, just to make him feel special. The fourth root of 10,000. Some of you might know that that's 10 to the fourth, so that's just 10. But you might break it up into the fourth root of 625 times 8, which would be broken up into the fourth root of 625 times the fourth root of 8. The fourth root of 625 is 5. That's not 8, that should be 16. You guys didn't catch me? And the fourth root of 16 is 2. So 5 times 2 would be 10, which is the fourth root of 10,000. What if I have, we had something like x to the third over y to the fifth to the fourth power. Did x to the third to the fourth power is x to the 12. Y to the fifth to the fourth power is y to the 20. What if I have the square root of x to the 8th over y to the 14th? Well, I can split that up to the square root of x to the 8th, x to the 8th, over the square root of y to the 14th. What is the square root of x to the 8th? Remember, square root of x to the 8th is asking what number squared equals x to the 8th. So in other words, what number to the power of 2 equals x to the 8th? That number would just be x to the 4th, right? 4 times 2 is 8. So the square root reverses that. So the square root of x to the 8th, we would divide the power by 2 to get x to the 4th. So with that, what would the square root of y to the 14th be? Y to the 7th. We've got to reverse that process. So we're dividing by 2. 14 divided by 2 is 7. So with that in mind, the fifth root of x to the 30th should be what? When it was a square root, we divided the power by 2. When it's a fifth root, we should divide the power by 5. 30 divided by 5 is 6. That's x to the 6th. So if I have the fourth root of x to the 24th over y to the 12th, what is the fourth root of x to the 24th? X to the 6th. Fourth root of y to the 12th. Y to the 3rd. Now I can't combine those any further. Some people think that, well, why can't I do 6 divided by 3 or 6 minus 3? Well, why can't we? Because this exponent has a base of y of x, and this one has a base of y. They have different bases, so we cannot combine their powers. Now, what if I take, somebody pick a number between 50 and 20. Not everybody at once. I'll go with 16. So how about we do the 16th root of 7 to the 16th power? What do you think that's going to be? If I did 7 times 16 and then divided by 16, what would I get? 7. Because multiplying by 16 and dividing by 16 are inverses. Power of 16 and a 16th root are inverses. So they cancel out, we get 7. How about the 12th root of 4,096 to the power of 12? What's that going to come out to be? You got it. Doesn't matter what order they come in, the 12th root and the 12th power are inverses. They cancel each other out. So if I am using this to solve an equation, I can look at something like this, and I'm going to take it apart. Now, what has happened here to build this equation? The first thing that would happen would be the exponent. So x was taken to the power of 4. Then multiplication, it was multiplied by 5. And the last thing that was happened to build this equation was 9 was added to it. Does that make sense? So the power of 4 times 5, and then add 9. Remember, when we solve an equation, we're taking it apart. And when you take it apart, the first piece that comes off is the last piece that was put on. So the first piece we remove is the adding 9. We do that by subtracting 9. 5x to the 4th equals 89. And then, divide by 5. Oops, that should be 80. 89 minus 9 is 80. Divide by 5, x to the 4th equals 16. And then the 4th root. You got it. So x equals 2, technically, or negative 2. Either one would make this a true statement, a true equation. If you guys just put down the positive 2, I'm okay with that for now. See if you can figure out how to enter this in your calculator. 25 to the power of 1/2. 5. How about 49 to the power of 1/2? Did you get to work, Jordan? Yeah? You sure? Or are you just going along with the crowd? Okay. Are you noticing a pattern here at all? Yeah. That power of 1/2 is equivalent to the square root. This is something that is that whole relationship between our powers and our inverses. If you remember back when we were doing addition and subtraction, we said that 7 minus 3 could be converted into 7 plus a negative 3. Does that look familiar? You could add the opposite. Multiplication and division. We said 8 divided by 2 could be thought of as 8 times the reciprocal of 2, or 1/2. Multiply by the reciprocal. Division is not an operation in itself. It's defined as part of multiplication. The same thing here. A 4th root of a number like 81 could be defined as 81 to the power of 1/4. So of course that's going to be 3 or negative 3. So what would it mean to have 125 to the power of 1/3. That's equivalent to what root? Cubed root, or third root of 125. So that's just 5. How about this? Oh, let's see here. Let's do 32 to the power of 2/5. Well, here we've got to do a little bit of reverse engineering. 32 to the 2/5. 2/5, we're going to write it like this. Now remember, when I have a power of a power, what do I do with those powers? I multiply them. 1/5 times 2 is 2/5. So this is equivalent to 32 to the power of 2/5. What this is telling me I can do is I can do that root first. What is the 5th root of 32? Say 2. 2. And then 2 to the power of 2, which is 4. Now, equivalent to that, however, is 32 squared, then to the power of 1/5. Is that the same thing? Yeah, because it's still 2 times 1/5 will be 2/5. So that means we can take 32 squared, which is 1,024, and then do a square root of it, which is a 5th root of it, which is 4. Notice we get the same result. So when we have a fractional exponent like that, it means two things are happening to our number. Eight to the power of 7/3 is saying one of two things is happening here. Actually, both are happening, but you can pick which way you want it to happen. It is either the third root of 8 to the power of 7. The denominator in that fractional exponent is the root. The numerator is the power of the exponent. Or you can say it's 8 to the power of 7 and then take the third root of that. Either way, it's going to be 128. Make sense? Okay. Well, I'm going to give you a packet here. It's going to be page 464 through 465, 1 through 43, the odd in the packet.